All right, so this week we start chapter 6, where we look at inverse, exponential, logarithmic functions, and how they're all related. So today we're going to start with inverse functions, which is 6.1. All right, inverse operations undo each other. So for example, you have addition and subtraction. 4 plus 5 is 9, and you can undo that by subtracting 5 and getting back to 4. Multiplying is the same thing. 3 times 2 is 6, and if we divide by 2, that brings us back to our original number, 3. So that's why they're inverse operations. All right. One-to-one functions. So if you remember, a function has one x for every y. So when you drew a shape, it passed the vertical line test. A one-to-one function also has one y for every x. So if we were trying to decide if these were one-to-one, we would look. So first, 3, 2, 4, 6, 1, 3, 1, 3. So whatever we put in for x gives us a y, so it is a function. And these are all different depending on the x. These two are the same, but they have the same x. So yes, this is one-to-one. If we look at b, it's a function because when you have the same x value, you have the same y. But it's not one-to-one because you get two different two of the same y value for different x's. So that makes it not one-to-one. If we were deciding if a function's one-to-one, there's a couple things you can do. One, you can try some numbers and see how they work. So if we plugged in a 3 and a -3, we get the same answer. So that means it's not one-to-one. So if you can plug in any y value or any x value and get the same y, if those are different x's, it's one-to-one. It's not one-to-one. Another choice is to graph. So if we graphed these two functions, -4x plus 12 or 2x to the third plus 5, let's see. Nope, still not what I want. What it looks like. So here, -4x plus 12 is going to be blue, and 2x to the third plus 5 is going to be red. So if we do this, I'm going to make my window a little bit taller here. Window 20, graph. All right, so we're going to do what's called the horizontal line test. If anywhere I can draw a horizontal line and touch the graph more than once, it's not one-to-one. So our cubic one flattens out, but the y does still change. If you watch that blue down in the bottom left of that. Oh, let me try this. Yeah, so this is still, the y is still changing as I move. So these both pass the horizontal line test, so they're both one-to-one. So if we look at this graph here, A, when we draw a horizontal line, it touches the graph in 3 places, not one-to-one. B, no matter where we draw that horizontal line, it only touches the graph once, so it is one-to-one. So if we go back and look at these two, what do you guys think? Yes or no for one-to-one? Well, the first one's a yes, because no matter where you go, you touch in one place. The second one, even though here you can touch in one, here you touch 3. So because even part of the graph doesn't pass the horizontal line test, it's not a one-to-one function. So just like inverse operations, inverse functions undo each other. So one way to look at that is f of g of x equals x. So remember, f of g, or fog, f of, well, let me write this again here. F of g of x is the same as f of g of x. So you're plugging x into g, then you're plugging that into f. So if it spits out x, it's an inverse function. Same thing goes the other way. So if we look at this, the blue line is x to the third minus 1. And g would be the cubed root of x plus 1. Are they inverses? So do they undo each other? So we're going to do that. Sorry, I had an email I had to answer. Our yearbook's due tomorrow. Okay, so if I graph the cubed root of x plus 1, it would look like this. Like that. I'm not the greatest drawer. So is that the inverse? Well, we can find out by plugging it in. So if f of g of x is going to equal x. So we got to plug g in. So if I take this and put it in here for x, and then subtract 1, let's do the math out. So the cubed root and the cubed are going to cancel each other out. So we get x plus 1 and then minus 1. And those cancel out and we get x. So they are inverses because mathematically, if I plug the g in, I get that. I get the x that I originally plugged in. When you have an inverse, it's written like this, f to the negative 1. But we read it as the inverse of x, so f inverse. Now, because these flip each other around, the domain and range is going to swap. So the domain of f is going to be the range of f inverse and vice versa. All right, so let's decide here if these are 1 to 1, and if they are, find the inverse. So if we look at A, we have two places where the y is 1, but our x's are different. So that tells us it's not 1 to 1. Maybe you notice these. The y's are the same, but the x is different. So that also proves it's not 1 to 1. Looking at B, all of our y's are different, so it is 1 to 1. To find the inverse, you flip all of your ordered pairs. So G inverse would equal 3, 1 becomes 1, 3. 0, 2 becomes 2, 0. 2, 3 becomes 3, 2. And 4, 0 becomes 0, 4. Now we have our inverse function. Analytically, you're interchanging x and y. So if you're doing points, you can do it just like that. If you're doing equations, you're going to switch your x's and y's and then solve for y. So let's try a couple. So we're trying to find the inverse. So first, if we looked at the graph, it passes the horizontal line test, so it's 1 to 1. So now, step 1, we're going to rewrite it, but instead of f of x, we're going to write y. And then we switch the x and y. So we're literally just writing them in a different order. Now we solve for y. So I'm going to subtract 5 from both sides. Divide everything by 2. And then rewrite it with f inverse. So that is our inverse function. This one, x squared plus 2, if I graphed that, it would look like this. This does not pass the horizontal line test, so it does not have an inverse. Okay, you try this one. All right, so first we're going to rewrite it as y equals. Then we switch our x and y. Then we solve. So to undo a cubic, we have to do a cubed root of both sides. Oops. Now we want to bring the 2 over. So cubed root of x plus 2 equals y. And then we just substitute y for f inverse. So it's the cubed root of x plus 2. So that is our inverse function. Graph of an inverse is a reflection across y equals x. So when you're switching your x and y's, that's how you know it's a function, the y and x flip. So it's also a reflection. So for example, if we were graphing this, we have the points -2, 0, -1, 1, 2, 2, and 5, root 7. So our inverse flips these points. So it trades the x and y's. And then we graph our new points. So I'm going to graph those in red. So 0, -2. And then 1, -1. And 2, 2. And root 7, 5. Well, that's not 5. Root 7, 5. So if we draw, that shape is flipped over the green line, which is y equals x. So analytically, we switch the x's and y's. Graphically, we reflect it over that line. Here is it drawn out all in the same color. All right, so let's do this one. Find the inverse, and then we'll talk about the domain and range. So we substitute the y. Then we switch our x and y. To undo a square root, we square both sides. Bring the 5 over, so we get x squared minus 5 equals y. If we substitute our inverse, it looks like this. Now, because the original had a range of 0 to infinity because of the square root, the domain of our answer has to be the same, 0 to infinity. Because remember, your domain becomes your range. So without that restriction, it wouldn't work. So you guys try this one. So we're going to switch. This one's a little more difficult because you end up with a couple y's, but it's not as bad as it looks. Multiply both sides by that denominator to get rid of it. Distribute. Now we want the y's on one side and the not y's on the other. So I'm going to subtract 2y to make it equal 0. Then I'm going to add x to both sides. So we get xy minus 2y equals x. Now, these terms have a greatest common factor of y. So I can factor that out and get x minus 2. Then divide everything by that. So we have a y equals now. Turn that into our inverse. And we have inverse of x is x over x minus 2. The big things you want to remember about your inverses. If f is 1 to 1, it has an inverse. The domain and range flip. So if the domain is the range for f, it's the inverse of f. It's the domain for the inverse. I don't know what I just said, but I'll say it again. Domain of f is the range of the inverse. And then if AB is a point, BA is on the inverse, and they reflect across y equals f. Y equals x. That's what's important.